All right, well, let's take a look at another example of work. So here we have two particles, are moving. That should be R, not at, H, are moving along two paths, C1 and C2. Now, on both of these paths, they are being affected by the following vector field. So, no matter what direction, the vector field is not going to change depending on the path. So the first part says we want to sketch the particles moving through space given the two paths. So here's path 1, notice they are parametric, and path 2, also parametric. So for path 1, I'm going to go ahead and graph this. At t equals 0, I can plug this in, and we are at the point 4, 0. At t equals 1, I can plug that in, and that's going to give me 3, 3. At t equals 2, that's going to put us at 2, and that's 8 minus 4. And at t equals 3, that's going to give us 1, 3 for our location. And I can plot this. We are at 4, 0, 1, 2, 3, 4. Then we're at 3, 3, 1, 2, and 3. So I kind of got my location up here. Then we're at 2, 4. Whoops. And then up here. And then we go down to 1, 3. So it almost looks kind of like it's parabolic probably. But there's our path. For C2, we can do the same thing. I can get my path. But this time we start at t equals 1. If we start at t equals 1, we're at the point 1, 3. And starting at t equals 2, we're at the point 2, 4. When t is 3, we would be at 3, 3. And you can verify these. And t equals 4, we're at 4, 0. Now right away I kind of notice it looks like they're going in the opposite directions here. But let's see. At t equals 1, so here we're at 1, 3, 1, 2, 3. At t equals 2, we're at 2 up 4. And at t equals 3, we're at 3, 3. And then at 4, 0. Yeah, it definitely looks like we're heading in the opposite direction. So that's one thing I kind of noticed right away is that we are heading in the opposite direction. So C1 and C2 are in opposite directions. So we're going to see about whoops, there it is. I think I got something on my pad there. Are in the opposite directions. Alright, so let's see what that might mean for us in just a few moments. So we want to calculate. So let's go and calculate the work done by our force field in the direction of motion. Now we typically do. These are sometimes called force field, or just count because we have a force applying on our vector on our field right here. So our rule here, F dot dr. Remember, we can't do dr. That's really hard. So we're going to use our other equation. What is that? F r prime dt. And we're going to use this a little bit easier. So let's take a look at curve 1. Now for curve 1, I know my time interval goes from 0 to 3. And I know my vector field. I know r is this 4 minus t, 4t minus t squared. I can get r prime pretty easily. I'm going to need r prime. That becomes negative 1. 4 minus 2t. All right, now the next thing we have to do is we have to convert our force equation into a parametric. And to do that, we can just replace, remember this is y. Well, there's my x value, there's my y value from my path. So, because remember, we're applying this force field to our path, so they're going to have the same y values. And at any given point, they're going to have the same y values, and they're going to have the same x values. So this is telling me to go y, which for us is going to be this. Whoops, sorry. It's going to be 4t minus t squared. And over here is plus x squared. And x squared is going to be this 4 minus t squared. To get our work equation, we have to dot these together. And if we do that, we're going to get, what's that, negative 1, 4 minus 2t. Dot that with 4t minus t squared, comma 4 minus t quantity squared. And that's going to become negative 4t plus t squared plus this 4 minus 2t times 4 minus t squared. And so our first work equation for path 1, so for path 1 our work equation would be integrated from 0 to 3, negative 4t plus t squared plus 4 minus 2t, 4 minus t squared dt. And oh look, I typed that in my brain and I get 69 over 2. Look how good I am. And then we're going to do the same thing for the next path. Well, for C2, our path, R of t, is t, comma, 4t minus t squared. We're going to need its derivative. That's just going to become 1, and then 4 minus 2t. We also need to parameterize our vector field. Remember, our vector field has to be on the same path. So this field is going to intersect this path. And so they have the same x values and the same y values. So my parameterization of my vector field, there's my y. Well, we're telling us in this case, y is 4t minus t squared. So we got this 4t minus t squared. And over here, x squared, well, here we're saying x is just t, so comma, t squared. Taking the dot product, r prime, whoops, sorry, I guess I should do it the other way. We want to take the dot product, take your force, vector force, dot that with r prime, because remember they are both vectors here. We dot those together, and I'm going to do this, this is going to be what, 1, 4 minus 2t, dot that with 4t minus t squared, comma t squared. And that winds up being 4t minus t squared minus, and this becomes t squared, plus t squared times 4 minus 2t. And this one's not that bad. We're going to get, when we simplify this, we get 4t minus t squared plus 4t squared minus 2t cubed, or this becomes 4t plus 3t squared minus 2t cubed. And remember, to get my work now, I am going to integrate this. In this case, our path goes from 1 to 4. 1 to 4, t equals 1 to 4. Don't forget your differential to dt. And again, this one's not that bad to solve. You can do this one by hand, much easier than the other one. But what we wind up getting is negative 69 over 2. Interesting. Take a look. I had opposite paths, but notice they have the same exact force. If I were to combine them, C1 plus C2, notice we get 0. We have a net force of 0, which we should expect, because going in the opposite direction should result in a 0 in the net force. Remember, we went in the opposite direction, but our force never changed. So we wound up with a net of 0 work done. That's why, like, when you go home and then you come back to school, you did no work. You have to do your homework. All right, so what does this say about the orientation of our paths? So let's talk about the orientation of the paths. And one, so if I have a vector field going in the same kind of general direction of our path. So let's say we have a vector field going, whoops, I guess I should do it right the other way. So if our vector field is in the same direction of our path, what we wind up with is positive work. So if the vector field is in the same direction of our path, R of t, work is positive. if our vector field is in the opposite direction of our path, then we get negative work. So if the vector field is in the opposite direction of the path, we get negative work. That's why you shouldn't go against your teachers, because that's negative work. And then the third option is what we have here. Well, if we get positive when in the same direction and opposite we get negative work, what does it mean when we get zero work? And most of you probably know this from physics, is that they're perpendicular. If the force is perpendicular to our path, we get, if the force is perpendicular to path, we get zero work. Now, we can actually kind of see that from our dot product. Remember, work is the dot product of our vector field dotted with our displacement vector. And from earlier this year, we learned how to get cosine of the angle. Remember the cosine of the angle? We had something on the bottom, but on the top, it was a dot product. And if that was zero, we know theta has to be 90 degrees. So we know if our work is zero, we know that our force is perpendicular to our path. All right, I hope you enjoyed the video. I'll see you guys later. Bye-bye. Well, come back for the next video. We'll see some more examples.